So I'll get started. The problem, of course, that we have in high energy physics, we'd like to use these billion-dollar colliders that we have to test hypotheses about nature. We don't have exact solutions to quantum field theories, neither for the standard model or beyond the standard model ones. So how do we make predictions to form reliable conclusions that we can really test theory against data? And so on the left-hand side here, I have kind of the main tool in our toolbox that we usually use. The first thing we do is that we start from perturbative approximation. We start by looking at fields, quantum fields as plane waves, non-interacting fields in the interaction picture, and then they just scatter off each other through relatively small, systematically calculable quantum corrections. And so that's nice. That gives us a way to relate Lagrangians, elementary fields, symmetries, interactions to rates, essentially rates for scattering reactions and decay rates and things like that. But of course, what we actually see in real life in these colliders is pictures like the one on the right. We see hadrons, hadronic final states. We're also colliding hadrons. So both the initial state and the final state at the LHC are these strongly bound states of quarks and gluons, which certainly have very little to do with quark and gluon plane waves. So how do we connect this confined world with our nice perturbative language in which we can solve things? So that's really the problem that I'm going to talk about. How do we connect the picture on the left with the picture on the right? So we can start by looking at a Parton. You've had some previous lectures on QCD, which I guess focused on the perturbative aspects, where we look at a Parton that's emerging from a hard scattering process or a decay process or something like that. So we've got a quark or a gluon coming out of a high energy, high PT scattering process. So hard means that it was created, kicked, with some large momentum transfer, much larger than a GeV, so much larger than the non-perturbative scale in QCD. And then you've probably heard about Parton showers already in the lectures. So accelerated charges give off radiation. That happens even in classical field theory. Shake charges, kick them around, they'll give off radiation. So we have these shower cascades. And at some point, we've described radiation. We start with ultraviolet chromodynamics radiation, and then we go down to low energy scales, long wavelengths. And at some point, these wavelengths are starting to get as big as hadrons of order, 1 GeV if we're in the momentum picture, or 1 femtometer if we are in space-time. And at that point, our perturbative description, we kind of know that perturbation theory, again, is built on these plane waves of asymptotic incoming and outgoing states. But if the wavelength starts to be long enough to big as a hadron, then we can't really use perturbation theory anymore. It's going to be bigger and bigger deviations, order 1 deviations. So what do? We've got these partons that have now radiated some gluons off. They all have wavelengths that are shorter than a proton. The quark is left over, or the original object here has lost some energy. And it's also, we've described all the processes that should be happening down to scales of order a GeV or an inverse GeV. So the simplest thing we could think of doing would be to say, okay, we've described all of these things. We know that the wavelengths, the characteristic wavelengths that we've gotten to are of order the size of a hadron. So let's just take each of these blobs that we have produced and call them a hadron. That sounds pretty stupid, right? I hope it sounds a little bit stupid. So in order not to sound stupid when we talk about this, we give it a very fancy name. We call it local Parton-hadron duality. Now we sound really smart, right? But that is essentially what local Parton-hadron duality, I mean, you can see it in the name, right? We take a Parton, replace it by a hadron. And you can sort of see that it's physically maybe not completely crazy, even though it's extremely simplified, and this is probably not what nature does. But local Parton-hadron duality is sort of the first concept you will come across if you study non-perturbative formalisms in high energy scattering problems. Okay, so the simulation version of local Parton-hadron duality is called independent fragmentation. It was something that people were doing decades ago. And so we have this fast Parton that comes out of our scattering process. It's created at a high scale. We call that the factorization scale. And then we say there's a fragmentation function that tells us, if we take a pion, so this quark, what's the probability that it'll fragment into a pion that carries a certain momentum fraction x of the original quark. So that's a probability distribution function that we can parameterize. It's intrinsically non-perturbative because it involves Parton to hadron transitions. We can give it some functional form, maybe motivated, or maybe just with machine learning, and we can fit these functions. And we know some things about these functions. If you start the quark out at a higher scale or a lower scale, there are equations that govern how this function should change as we change the scale Q. So that's called fragmentation functions. You may have heard of them in the perturbative part. If not, don't worry too much. So again, the fragmentation function is in principle an analytical object. If you turn this into a Monte Carlo model or a simulation model, it's called independent fragmentation. And in fact, even Pythia was doing independent fragmentation in the very earliest, before we did string fragmentation. And so November 1978, this is the first sort of Pythia version for quark jet generation. And they said, what in the abstract, a Monte Carlo computer program is presented, simulates the fragmentation of a fast parton into a jet of mesons. And that's basically still how we use Monte Carlos today. That is still the main purpose, if you're an experimentalist at least, or a phenomenologist who wants to take a hard scattering process, you want to fragment it into jets. Now, I would normally not include source code on slides because it bores the crap out of everyone. But in 1978, things were simple enough that this could actually be included in the appendix of the paper. And that is the first sort of fragmentation routine that was in any sort of Pythia family. It's Fortune 77, and I don't require you to be able to read it, but it's very simple. If you know C or anything like that, this will be pretty easy to see. It starts out with a quark, the hard parton. Then you create another quark-antiquark pair behind it, and you give it some random PT with some cos and sine, a random angle. You pair the antiquark and the quark up into a meson. So, and it can be a spin 0 meson or a spin 1 meson, so you give it some spin. You look up what its mass should be, and then you know how much transverse momentum that meson should take. So you give it some energy there. I'll get back to what this is in modern formulations. That particle could be a rho, then you do rho to pi pi or something like that. It can decay. And then you have your leftover quark here. If that has enough energy left to fragment more, you go back to step 2, go to 100, right? And you go back and then you create another meson. And so you can see how an initially very energetic quark gets chopped into smaller and smaller pieces, and eventually there's no energy left over. So that's a very simple fragmentation routine, and it's very similar principles that Pythia still operates on today with more sophisticated physics. Now, of course, as a physical model, local parton hadron duality doesn't make any sense. We took a parton, which has color, and we turned it into a bunch of hadrons, which don't have color. So we've just violated color conservation. If there's anything that you really want in QCD, it would be color conservation. Otherwise, you're breaking QCD. And also the whole point of confinement, if you want an actual physical model of what's going on, it's color confinement. It's the fact that the parton is colored that means that it should be confined into hadrons. So forgetting about color is a little bit unphysical, quite unphysical here. Physical model should involve at least 2 partons that have opposite colors, color-connected partons with opposite color charges. And so, we have a Z decay to QQ bar or scattering process. And these partons start separating. They have a perturbative era of radiation, but it's not just one parton. Even in parton showers, you will have heard probably about dipoles and these soft radiation patterns, that it's actually parton pairs that are radiating, not individual partons. And then at some point, when these 2 color-connected partons are far apart, some strong force field starts building up between them, and it's the force field between them, not the fragmentation of an individual parton, that we actually want to describe in terms of a physical model. Okay, so what do we know about that? On the lattice, in these lattice QCD simulations, so we can't do non-perturbative analytical calculations, but we can take the QCD Lagrangian, we can put it on a big space-time cube, and we can directly simulate what the action looks like, how it fluctuates, gluon fields, and so forth, just cranking the wheels. That's a very sophisticated topic, lattice QCD. I will not say anything about it because I don't know very much about it, but I will use the results. So these are non-perturbative calculations with some systematics attached to them because you have discretized space-time and so forth. So there's some uncertainties, but within the limits of what you can calculate in this setup, you are getting honest information about non-perturbative quantities. So one thing they can compute is they can compute the potential energy of a color singlet QQ bar state as a function of the distance between the quarks. So basically what they do is they take an infinitely heavy quark, color triplet charge, an infinitely heavy anti-triplet, and they put them some fixed distance apart. And then they run the QCD evolution equations, the equations of motion, and they can measure what is the potential energy of this configuration. Then they move the quarks and they measure it again, and they move the quarks and they measure it again, and then they can plot the potential between a quark and an anti-quark out. And this is what it looks like. So you can see that at very short distances, there's a sort of 1 over R type potential, just like a Coulomb potential. This is the QCD Coulomb potential. But a Coulomb potential would just flatten off at long distances, and charge at one end of the universe, an electric charge wouldn't feel an electric charge at the other end of the universe. But in QCD, that doesn't happen. We have this linear rise of the potential between the two. So there's a potential that just keeps growing between them as we separate. So there's an empirical model for that called the Cornell potential, which just sandwiches or combines a Coulomb type potential with a linear potential. And this kappa here, the slope of the linear potential, is exactly of the kind of dimension that you would expect for hadronic quantities, 1 GeV per Fermi. So that's how much energy these quarks has to deliver to the field between them as they are moving apart. Incidentally, that's quite a lot. If you translate it to SI units, that sort of tension is enough to lift a 16-ton truck against the pull of gravity. So if a quark tries to escape a proton, that is the force that pulls it back. So that's really a strong force. So at long distances, we have a picture where the force field is not Coulomb-like. It's not field lines spreading out all over the vacuum, but there's something else going on. Now, of course, if you're a physicist, so this is an honest calculation. It's lattice QCD. It's not a phenomenological model. It's the actual QCD Lagrangian, or close to it, something called the quenched approximation. That has been simulated on the lattice. But then if you show a physicist the potential, they will say, okay, I can build a model now if I know what the potential is, right? And the only model that we always use is a harmonic oscillator. Everything is a harmonic oscillator if you look close enough. Everything in the universe is a harmonic oscillator because we have, a quadratic approximation at the bottom of a potential, except one potential. This one. A linear potential does not have a quadratic dependence. So this is the only system that's different from a harmonic oscillator. Does anyone know what a linear potential is? It's a string. It's a string potential. So that's what motivates the string model of hadronization. Did you have a question? Okay. It's a string with a constant tension. So it's exactly the same that motivates string theory and so forth. It's the same developments. In the old days, in the 70s, QCD and string theory were basically the same thing. And people were using the same models, trying to figure out models of hadrons. And then eventually, when they started realizing these QCD behaviors are like strings, and they started studying string worldsheet theories, then one of the first things that happens on a string worldsheet is that the Einstein equations just come out. And then people were like, oh, this is amazing. And then they went off and did, string theory as a fundamental theory, but it still survives also in QCD, sort of old-fashioned string theory. It's not superstrings. But because of this linear potential, it's the phenomenological model that we think describes the physics at long distances, the linear part of the potential best. So this motivates then a model, right? So we go from the lattice. There's a few other things that we know about non-perturbative QCD that we really know. And now we go into model building land. We say, okay, I know the potential. I'm going to build a model based on this observation. So I'm now losing my direct connection to the Lagrangian of QCD, and I'm building a phenomenological model on what I know. So we let the color field between each pair of color-connected charges collapse into a narrow flux tube. So this sort of the limits of this force field here, where it becomes infinitely long and infinitely narrow, which is good if the longitudinal degrees of freedom are much higher than the short degrees of freedom. So this is for hard scattering processes where the quarks will move much further than 1 femtometer before they lose all their kinetic energy. And the transverse size of the flux tube is probably of order 1 over lambda QCD. So in the sort of textbook limit where we do this infinitely much, this is just a relativistic 1 + 1 dimensional world sheet, which is a string. So this is moving just like a particle has a world line, a string has a world sheet. And of course, if we looked closely enough at this, if we really zoomed in on it, we would find the extra dimension, the transverse size of the flux tube. There would be 2 extra little dimensions in there. So the 1 + 1 is a long distance kind of behavior of this object, but there would be 2 little dimensions inside that sort of we could see if we looked at it closely enough. There are things we're neglecting here. We're neglecting the width. We're neglecting the Coulomb part of the potential. We're just doing this as a string model now, and so there would be some endpoint effects that maybe we would have to worry about at some higher level of precision or whatever. So it's always important to know what one is throwing away. But this idea that we have a string world sheet should have something to do with the long-distance asymptotic physics, which is precisely what perturbation theory doesn't catch.